Picture this. It is the year 2003. A team of materials scientists at the University of Cambridge has just received a sample of ancient Roman glass. A small, greenish fragment pulled from an archaeological site near Naples. They are not art historians. They are not archaeologists. They are engineers. And they have one specific mission: figure out how the Romans made this. They have electron microscopes. They have X-ray diffraction equipment. They have spectrometers that can detect individual atoms. They have every tool that 21st century science has produced. And after months of analysis, after running the sample through every test in their arsenal, they come to a conclusion that nobody in that laboratory expected. They cannot reproduce it. Not exactly. Not with the same structural properties. Not with the same optical qualities. Something about the way those Roman craftsmen worked their glass 2,000 years ago, without electricity, without digital thermometers, without any of the precision instruments we consider absolutely essential, produced a material that modern engineers, with all their technology, have been unable to perfectly replicate. That story is not an exception. It is a pattern. And that pattern is one of the most unsettling, most fascinating, most scientifically provocative puzzles in all of human history. We live in an age of extraordinary technological confidence. We have sequenced the human genome. We have landed rovers on Mars. We have built artificial intelligence systems that can write poetry and diagnose cancer from a single medical scan. We tend to assume, almost unconsciously, that we are the smartest, most capable humans who have ever lived. That everything which came before us was cruder, simpler, less sophisticated. But what if that assumption is wrong? What if, scattered across the ancient world, buried under desert sands, locked inside museum display cases, etched into the walls of temples that were old before Rome was founded, there are technologies so advanced, so precisely engineered, so mysteriously effective, that our best scientists in 2026 are still scratching their heads, still running experiments, still coming up short. Today, we are going inside 7 of those technologies. Not the vague, mystical versions you might have seen on late-night cable documentaries. Not the pseudo-scientific theories about lost civilizations and alien architects. We are going to look at the actual science, the real laboratory results, the peer-reviewed papers and the honest admissions from researchers who expected easy answers and found something far more complicated. This is not a story about magic. This is a story about genuine scientific mystery and the humbling realization that human ingenuity has deep roots that we are only beginning to understand. Let us start at the beginning. Roman concrete, the material that gets stronger with age. Somewhere along the coast of Italy, about 80 kilometers north of Rome, there is a harbor that has been sitting underwater for 2,000 years. The harbor at Caesarea Maritima, the port structures at Baiae, the ancient piers at Pozzuoli. These Roman maritime constructions have been submerged in seawater, one of the most corrosive, destructive environments on the planet, for 2 millennia. And here is the part that makes modern civil engineers deeply uncomfortable. They are not crumbling. In fact, by certain measurable metrics, they are getting stronger. This is not a metaphor. This is not poetic exaggeration. This is a finding published in the journal American Mineralogist in January of 2017, based on research conducted by a team led by Marie Jackson at the University of California, Berkeley, in collaboration with researchers from laboratories in Italy, Sweden, and the United States. What they discovered when they analyzed cores drilled from these ancient harbor structures changed the way materials scientists think about concrete and raised a question that the construction industry is still trying to fully answer today. But to understand why this finding is so remarkable, we need to go back to basics. we need to understand what concrete actually is, why it fails, and what made the Roman version fundamentally different. Modern Portland cement, the concrete that holds up virtually every building, bridge, and infrastructure project in the contemporary world, works through a chemical process called hydration. You mix the dry cement powder with water. It undergoes a series of chemical reactions, and it hardens into a rigid matrix. The result is strong in compression, meaning it resists being crushed. But it has a critical weakness. It is brittle. It cracks. And when water gets into those cracks, carrying dissolved salts and minerals, the degradation accelerates. The steel reinforcement bars inside modern concrete corrode. The cracks widen. The structure weakens. The American Society of Civil Engineers has repeatedly documented that the United States alone spends hundreds of billions of dollars every decade repairing and replacing concrete infrastructure. Bridges, roads, water treatment plants. The material we build civilization with has a fundamental flaw baked into its chemistry. The Romans used something different. Their concrete, called opus cementitium in Latin, was made from a combination of volcanic ash, seawater, and specifically, they used a particular type of volcanic ash called pozzolana, named after the town of Pozzuoli near Naples, where it was quarried in enormous quantities. They mixed this ash with lime and seawater, then packed it with chunks of volcanic rock called tuff. For centuries, historians and engineers knew that Roman concrete was durable. The evidence was literally everywhere. In the Pantheon, which has been standing since approximately 125 AD and still holds the record as the world's largest unreinforced concrete dome. In the Colosseum, in the road networks and aqueducts that crisscrossed the ancient empire. But the assumption was that this durability was simply a matter of thick construction. Build it massive enough, and it will last. Add enough material, and time cannot touch it. The 2017 study blew that assumption apart. When Jackson and her team drilled into the submerged harbor structures and analyzed the samples at the Advanced Light Source Synchrotron at Lawrence Berkeley National Laboratory, a particle accelerator that can probe materials at the atomic level, they found something extraordinary happening inside the ancient concrete. The seawater was not destroying the material, it was reacting with it. Specifically, the seawater was interacting with the volcanic ash matrix and producing new crystals of a mineral called tobermerite, a rare, exceptionally strong crystalline structure that was filling in microscopic gaps and cracks in the concrete, reinforcing it from the inside. Read that again. The seawater was making the Roman concrete stronger. The chemical process, as Jackson's team described it, involved aluminum atoms from the volcanic ash substituting for silicon atoms in the tobermerite crystal structure, creating what they called an al-tobermerite phase. This substitution made the crystals more resilient and better able to reinforce the surrounding matrix. It was a slow process, occurring over decades and centuries, but it was continuous. The concrete was, in a very real sense, self-healing. By 2023, a follow-up study published in the journal Nature Communications, again involving Jackson and an expanded international team, provided additional evidence of this mechanism and analyzed additional Roman sites around the Mediterranean. The findings were consistent. Roman marine concrete structures showed mineralogical evidence of ongoing strengthening reactions, even after 2,000 years of seawater exposure. Now here is where the story gets genuinely uncomfortable for the modern construction industry. We cannot make this material. Not yet. Not at scale. Oh, we understand the chemistry now. Jackson's team has done extraordinary work reverse engineering the basic mechanism. Several research groups, including teams at MIT, at ETH Zurich, and at universities in Australia, have published papers describing how to recreate pozzolanic concrete using volcanic ash or similar silica-rich industrial byproducts like fly ash from coal power plants. And in controlled laboratory conditions, researchers have produced small samples of concrete that show similar mineralogical properties to the Roman material. But laboratory samples are not harbor walls. They are not domes spanning 43 meters without a single supporting column. The gap between producing a cubic centimeter of material in a laboratory and deploying it reliably at architectural scale across varying temperatures, mixing conditions, curing times, and load requirements is enormous. There is also the question of the Romans' specific knowledge of materials and proportions. We know they used pozzolana. We know they used lime and but the exact ratios, the specific techniques for mixing and placement, the understanding of curing conditions that guided Roman engineers, that knowledge was not written down in a form we have recovered. It was craft knowledge, passed from master to apprentice across generations, and at some point in the centuries following the collapse of the Western Roman Empire, that chain of transmission broke. Lynn Lancaster, an architectural historian at Ohio University who has written extensively on Roman concrete construction, has pointed out something important in her research. The Romans themselves did not fully understand why their concrete worked the way it did. They discovered through empirical observation, through building things, watching what happened, and adjusting their methods, that certain volcanic ashes from certain regions produced superior results. They codified this knowledge as practical craft, not theoretical chemistry. They were engineers before they were scientists. And their engineering, tested over centuries of trial and error, arrived at solutions that modern materials science is only now beginning to explain. There is another layer to this story that rarely gets mentioned in the popular accounts, and it matters enormously for understanding the scale of the challenge. Modern concrete production is one of the largest sources of carbon dioxide emissions on the planet. The process of heating limestone to produce Portland cement clinker releases massive amounts of CO2, roughly 8% of global human emissions annually, according to estimates from the International Energy Agency as of 2024. The construction industry has been searching urgently for lower carbon alternatives for decades. Roman-style pozzolanic concrete could, in principle, be produced with dramatically lower emissions, because it does not require the high-temperature calcination of limestone in the same. The volcanic ash does much of the chemical work that heated limestone clinker does in Portland cement. This is not a trivial point. If materials scientists can crack the remaining engineering challenges, if they can reliably reproduce Roman concrete's properties at industrial scale, the implications for global construction and for carbon emissions could be profound. Several startups and research consortia have been working toward exactly this goal. A company called Calix, based in Australia, has been developing processes for producing reactive magnesia and lime-based cements with lower emissions profiles. Groups at MIT's Concrete Sustainability Hub have published research on incorporating volcanic ash and industrial pozzolans into concrete mixes. The European research program GeoCon has explored geopolymer concretes inspired in part by ancient Roman formulations. But as of early 2026, no one has produced a commercially deployed, large-scale concrete system that fully replicates Roman marine concrete's extraordinary longevity and self-strengthening properties. The chemistry is better understood. The engineering challenges remain substantial. And out there, under the Mediterranean, those ancient harbor walls keep doing their thing, slowly growing stronger. Crystals propagating through the matrix, filling gaps, reinforcing connections, performing a materials science trick that 2,000 years of intervening human civilization has not yet fully figured out how to copy. Think about that for a moment. The harbor at Baiae has been underwater since roughly the 2nd century AD. It has survived earthquakes, volcanic activity. This is the Campi Flegrei region, one of the most geologically active places in Europe. Storms, ship traffic, saltwater corrosion, and the slow grinding passage of 2,000. A comparable modern concrete structure built with the best materials available today would typically be designed for a service life of somewhere between 50 and 100 years before requiring significant repair or replacement. 2,000 years versus 100 years. That is not a marginal difference. That is not a matter of the Romans simply building thicker. That is a fundamental difference in material behavior, and it is a difference we are still working to understand and replicate. There is one more element of the Roman concrete story that deserves attention, because it speaks to something deeper than materials science. When Jackson's team published their 2017 findings, the response from the scientific community was not uniform acclaim. Some researchers pushed back, arguing that the Tobermoryite formation they observed might not be as structurally significant as claimed, or that the specific conditions of volcanic harbors might not translate to other construction applications. This is how science is supposed to work. Challenge the findings. Demand replication. Look for alternative explanations. And what happened over the subsequent years was the kind of scientific process that, when it works properly, is genuinely beautiful. Independent teams in different countries ran their own analyses. Some confirmed the core findings. Others raised additional questions about the specific mechanisms involved. The picture became more nuanced, more complex, and ultimately more accurate. By 2025, the scientific consensus, still evolving, still debated at the margins, was that Roman marine concrete does indeed show evidence of strengthening mineralogical reactions driven by seawater interaction, that this is a genuinely unusual and valuable property, and that modern materials science has not yet produced a synthetic equivalent that matches it across all relevant performance parameters. The Romans built something we cannot fully replicate. And the harder question, the one that keeps material scientists up at night, is this: how many other things did they know that we have forgotten? That question is going to follow us through every chapter of this video, because concrete is just the beginning. Damascus steel, the blade that should not exist. In the spring of 2006, a small package arrived at the Institute for Technical Physics at the Technical University of Dresden, Germany. Inside was a fragment of a blade. Not a modern blade, an ancient one. A piece of a genuine Damascus steel sword, acquired through an archaeological collection, its surface marked by the unmistakable visual signature that had made this material legendary across the medieval world. A flowing, rippling pattern of light and dark bands, like frozen waves moving through the metal, like the surface of water caught in a moment of perfect stillness. The scientists waiting for that sample were Peter Paufler, a crystallographer, and his colleague Stefan Roth. They were not historians. They were not weapons enthusiasts. They were physicists, and they had a specific, technically precise question they wanted to answer. They wanted to know what was inside. What they found, using a combination of X-ray diffraction analysis and high-resolution electron microscopy, was something that should not have existed in a medieval sword. Something that the scientific community, when the results were published in the journal Nature in November of 2006, described with a kind of barely concealed astonishment. Carbon nanotubes. Structures measuring just a few nanometers in diameter, billionths of a meter, woven through the metal matrix of a sword forged somewhere in the Middle East between roughly the 3rd century and the 17th century AD. Carbon nanotubes, one of the most extraordinary materials in modern nanotechnology. First formally described by Japanese physicist Sumio Iijima in 1991, Nobel Prize territory, the subject of billions of dollars of modern research investment. Inside a medieval sword. Let that land for a moment. Carbon nanotubes are cylindrical structures made of carbon atoms arranged in a hexagonal lattice, rolled into tubes so small that thousands of them laid side by side would not span the width of a human hair. They are extraordinarily strong, stronger pound for pound than steel by an enormous margin. They conduct heat and electricity with remarkable efficiency. They are, in many ways, the wonder material of 21st century nanotechnology. We use sophisticated chemical vapor deposition processes, vacuum chambers, and precisely controlled temperatures to produce them deliberately. Medieval sword makers were producing them accidentally. Through a process of ore selection, charcoal smelting, and repeated heating and working of metal that had been refined empirically over generations, with no knowledge of atomic structure, no electron microscopes, no concept of nanotechnology, craftsmen in regions of South Asia and the Middle East were creating conditions that caused carbon atoms to self-assemble into these extraordinary structures inside the metal. And the result was a blade that, by the accounts of everyone who encountered it, Arab scholars, Crusader knights, European traders, Persian historians, was unlike anything else in the medieval world. To understand why Damascus steel was so exceptional, you need to understand the fundamental challenge that faced every sword maker throughout history. Steel is an alloy of iron and carbon. The carbon content determines almost everything. Too little carbon, and you have iron, relatively soft, prone to bending, holds an edge poorly. Too much carbon, and you have cast iron, extremely hard but dangerously brittle, liable to shatter under impact rather than flex. The entire art of historical metallurgy was a constant negotiation between hardness and flexibility. You needed a blade that could hold a sharp edge, which required high carbon content, but that would not snap when it hit armor or bone, which required lower carbon content. The ancient solution across most of the world was layering. Japanese swordsmiths folded and welded together layers of high carbon and low carbon steel, creating a blade with a hard cutting edge and a more flexible spine. European smiths developed their own variants of pattern welding. These were sophisticated techniques, producing excellent weapons. But Damascus steel, specifically the type made from a particular ore called woots, imported primarily from regions of southern India, Sri Lanka, and parts of Central Asia, achieved something different. It achieved high carbon content throughout the blade, carbon levels that should have produced brittle, unusable metal, while somehow maintaining extraordinary toughness and flexibility. Historical accounts describe Damascus blades capable of cutting through a floating silk scarf, a test of edge sharpness, and simultaneously withstanding impacts that would have shattered ordinary high-carbon steel. The combination was, by the metallurgical standards of the time, impossible. How? This is where the story becomes a genuine detective tale, because the answer took the scientific community decades to piece together, and involves a cast of researchers spanning multiple countries, multiple disciplines, and multiple failed attempts. The first serious modern scientific investigations of Damascus steel began in the 1970s. John Verhoeven, a metallurgist at Iowa State University, and Alfred Pendray, a bladesmith, began what would become a decades-long collaboration, attempting to understand and reproduce the material. Their work, published across several papers culminating in a landmark study in the journal Metallurgical and Materials Transactions in 1998, established several crucial facts. First, genuine Damascus steel, what they called Woots Damascus, was distinct from pattern-welded steel, despite the two often being confused. Pattern welding creates the appearance of flowing surface patterns through mechanical working of different steel types. Woots Damascus creates those patterns through a completely different mechanism: the formation of iron carbide bands called cementite within a high-carbon steel matrix, produced during specific cycles of heating and cooling. Second, the production of genuine Woots Damascus required a very specific type of ore that contained trace amounts of particular elements including vanadium, chromium, manganese, cobalt, and nickel in precise combinations. Verhoeven and Pendray discovered this through a painstaking process of testing different ore sources and comparing the results. Ores from certain regions of India produced the characteristic Damascus patterns. Chemically similar ores from other regions did not. Third, the specific heating and cooling cycles used by historical craftsmen, the temperatures reached, the duration of each phase, the rate of cooling, were critical. Small deviations produced dramatically different results. Verhoeven and Pendray eventually produced blades that displayed visual patterns similar to genuine historical Damascus steel. They published their results. They demonstrated their methods, and the bladesmith community. There are dedicated craftspeople around the world who have spent careers attempting to reproduce Damascus steel, recognized their work as a genuine. But then came the Dresden paper in 2006, and the carbon nanotube finding added a layer of complexity that the existing model had not accounted for. If carbon nanotubes were present in historical Damascus blades, and Poffler and Roth's electron microscopy evidence was compelling, then the material was not simply a matter of iron carbide band formation. Something was happening at the nanoscale that the existing metallurgical models did not fully explain. The nanotubes were almost certainly not being produced intentionally. The craftsmen had no concept of nanotechnology. But the specific combination of high-carbon ore, particular trace element chemistry, cyclic heating with wood and charcoal that would have produced carbon-rich gases, and the slow cooling rates used in traditional smithing. This combination appears to have created, inadvertently, conditions under which carbon atoms could form nanotube structures. The implications of this are fascinating on multiple levels. On a practical level, it suggests that the extraordinary mechanical properties of Damascus steel, its combination of hardness and toughness, may have been partially a consequence of nanotube reinforcement of the metal matrix. Carbon nanotubes are extraordinary mechanical reinforcers. If they were distributed through the blade structure, even in small quantities, they would have contributed to the material's performance in ways that contemporaries could observe empirically. This blade is better than that blade, without understanding why. On a scientific level, it raises a genuinely startling. If medieval craftsmen were accidentally producing carbon nanotubes through empirical metallurgical practice, what does that tell us about the potential to accidentally discover nanotechnology through other pre-modern processes? What other ancient materials might contain nanoscale structures we have not yet looked for? And on a cultural and historical level, it is a reminder that the loss of Damascus steel production was not simply the loss of a craft technique. It was the loss of a complex system of knowledge involving ore sourcing, heat management, material selection, and generational transmission of empirical wisdom that encoded, without understanding it, genuine nanomaterial science. Because Damascus steel production did stop, sometime around the mid-18th century, the production of genuine Wootz Damascus blades ceased. The exact reason is still debated. The most widely accepted explanation is that the specific ore deposits that provided the critical trace element chemistry were exhausted or became inaccessible due to trade disruptions. Without the right starting material, the process could not be replicated, because craftsmen had not written down the specific ore requirements, only the processing methods. When the ore changed, the results changed, and no one understood why. By the time European metallurgists began seriously investigating Damascus steel in the 19th century, trying to reverse engineer a material they recognized as exceptional, the knowledge chain had broken. The craftsmen who might have explained the specific ore sourcing and the precise heating protocols were gone. This brings us to the current state of the science, and it is more complex than either the enthusiastic nanotechnology headlines or the skeptical metallurgist responses suggest. Several research groups have, since 2006, attempted to deliberately produce steel containing carbon nanotubes. A team at the Leibniz Institute for Solid State and Materials Research in Dresden published work in 2012 describing synthesis of nanotube-containing steel using modern controlled processes. The nanotubes were produced. The steel was harder and tougher than equivalent material without nanotubes. But no one has yet produced a material that matches historical Damascus steel across all its performance characteristics: the specific carbide banding pattern, the edge retention, the toughness, the visual surface patterns, simultaneously, reliably, and at the quality level represented by the finest historical examples. The Verhoeven-Pendray method produces blades that resemble Damascus steel in appearance and share some of its microstructural features. Modern research into nanotube-reinforced steel has produced materials with enhanced mechanical properties. But the full package, what the actual historical Damascus blade was and why it performed the way it did, remains a partially solved problem. There is also an important scientific caveat that honest discussion of this topic requires acknowledging. The 2006 Poffler and Roth study, while published in Nature and widely cited, has been the subject of some scientific debate. questions have been raised about whether the nanotube structures observed were representative of Damascus steel broadly, or specific to the particular sample analyzed. Whether they were formed during the original smithing process or through subsequent transformation of the metal over centuries, and what their actual contribution to the blade's mechanical properties was, as opposed to the well-documented iron carbide banding. These are legitimate scientific questions. The nanotube finding has not been comprehensively replicated across a large sample of Damascus steel specimens, in part because genuine historical specimens are rare and valuable, and cutting them up for analysis is something museum curators understandably. What the scientific community agrees on is this: Damascus steel had extraordinary properties. Those properties emerged from a complex, empirically developed manufacturing process that encoded material science we are still working to fully understand. The loss of that process represented the loss of genuine technical knowledge. And despite decades of serious scientific and craft effort, no one has yet produced a material that is, in every measurable sense, equivalent to the finest historical examples. A medieval sword that contained nanotechnology, a manufacturing process that encoded material science without understanding it, and a mystery that has occupied metallurgists, physicists, and bladesmiths for the better part of a century. Damascus steel is not a myth. It is not pseudoscience. It is a real material with real, measurable properties. And it is a material that our best modern science is still struggling to fully explain, let alone replicate. The blade that should not exist is sitting in museum collections in Istanbul, in London, in New York, and in Tehran. You can look at it through glass. You can see the rippling patterns on its surface. And somewhere inside that metal, at scales far too small for the human eye to detect, structures that we associate with cutting-edge 21st century nanotechnology are waiting, silently, patiently, for us to figure out how they got there. Greek fire, the weapon that burned on water. Constantinople, 678 AD. A massive Arab fleet is closing in on the city. Hundreds of ships, thousands of warriors, the full military weight of the Umayyad Caliphate bearing down on the walls of the Byzantine Empire's capital. By any conventional military calculation, the city should fall. Then the Byzantine ships deploy something the Arab sailors have never seen before: a liquid, launched from bronze tubes mounted on the prow of Byzantine warships, that ignites on contact with water. Not despite the water, because of it. The flames spread across the surface of the sea itself. Ships burn. Men burn. Attempts to extinguish the fire with water make it worse. The Arab fleet is destroyed. Constantinople survives. The weapon is called Greek fire, and 1400 years later, we still do not know exactly what it was. This is not a case of poor historical documentation. Byzantine sources describe Greek fire extensively. Arab chroniclers who survived encounters with it wrote about it in detail, with a combination of military respect and barely concealed terror. The weapon was used repeatedly over several centuries. At the Siege of Constantinople again in 717 AD, during various naval engagements throughout the 9th and 10th centuries, and each time the accounts are consistent. It burned on water. It could not be extinguished with water. It clung to surfaces. It was projected as a liquid stream under pressure. And it was so militarily decisive that the Byzantine Empire treated its formula as the highest state secret, more carefully guarded, according to historian John Haldon of Princeton University, than virtually any other piece of strategic knowledge the empire possessed. The formula died with the empire. Constantinople fell to the Ottoman Turks in 1453 AD, and whatever knowledge of Greek fire's composition had survived to that point vanished into history. What followed was one of the longest-running chemical detective stories in the history of science. The core question seems straightforward. What substance burns on water and cannot be extinguished by it? Modern chemistry gives us several candidates, and researchers over the past century and a half have proposed most of them. The oldest and most persistent theory involves quicklime, calcium oxide, which reacts violently and exothermically with water, generating intense heat. Mix quicklime with an oil-based fuel, the theory goes, and contact with water would ignite the mixture. This hypothesis has been around since the 19th century and has the advantage of being chemically plausible with materials available in the Byzantine world. A second major theory centers on naphtha, a petroleum distillate available from natural seeps in the region around the Black Sea and in parts of the Middle East. Naphtha is flammable, it floats on water, and it was known to Byzantine chemists. The historian and chemist J.R. Partington, in his landmark 1960 study of Greek and Roman military technologies, argued that Greek fire was essentially a sophisticated naphtha-based incendiary, possibly thickened with resins and enhanced with other additives. A third hypothesis, proposed by British historian and chemist John Haldon and his colleague Maurice Byrne in a 2006 paper published in the journal Byzantine and Modern Greek Studies, involved a combination of pine resin, naphtha, calcium phosphide, and possibly saltpeter, a mixture that would produce self-igniting, water-reactive incendiary properties. The problem is that none of these theories fully accounts for all the properties described in historical sources. Quicklime generates heat on water contact, but the self-sustaining flame described in Byzantine accounts requires an additional fuel component that the quicklime theory alone does not cleanly explain. Naphtha burns on water. It floats and ignites, but it does not react with water in a way that makes water an accelerant rather than an extinguisher. The Haldon-Byrne calcium phosphide hypothesis is chemically interesting, but requires phosphide compounds whose production in the Byzantine world would have been technically challenging to document. The University of Athens Chemistry Department conducted experimental reconstructions in the 1990s, testing several proposed formulations. Their results, while not published as a formal peer-reviewed study, were reported in the proceedings of a Byzantine Studies conference. Some formulations produced impressive incendiary effects, but none perfectly matched all historical descriptions simultaneously. In 2022, a team at the Aristotle University of Thessaloniki published a more systematic experimental study in the Journal of Archaeological Science, testing multiple proposed formulations against the specific performance criteria described in Byzantine military manuals, particularly the Tactica of Emperor Leo VI, written around 900 AD, which provides some of the most detailed technical descriptions of Greek fire deployment. Their conclusion was carefully worded. Several formulations could reproduce individual properties of Greek fire, but no single tested formulation reproduced all documented properties simultaneously. There is also the delivery system to consider. Because Greek fire was not simply a substance, it was a weapons system. Byzantine sources describe pressurized bronze siphons, handheld projectors for infantry use, and ceramic grenades filled with the mixture. The engineering of a system capable of projecting a burning liquid under pressure at sea on wooden ships without catastrophically destroying the launch vessel represents a significant technical achievement independent of the chemical formula itself. Anna Komnene, the 12th century Byzantine princess and historian, whose Alexiad is one of our most detailed sources on Byzantine military technology, describes the siphons as producing a continuous stream of fire that could be directed at specific targets. This implies a level of pressure and flow control that was not trivial to engineer with medieval materials. What makes Greek fire particularly fascinating from a modern scientific perspective is what it tells us about Byzantine empirical chemistry. The Byzantines did not have modern organic chemistry. They did not understand combustion at a molecular level. But through centuries of empirical experimentation, testing materials, observing results, refining formulations, they arrived at a chemical system whose precise nature we cannot determine even with modern analytical tools, because we have no surviving samples to analyze. Damascus steel at least left us physical artifacts. Roman concrete left us harbor walls. Greek fire left us only words, and those words describe something our chemistry can approach but not definitively identify. The honest scientific position, as of early 2026, is this. We know Greek fire was real. We know it had extraordinary incendiary properties. We have several chemically plausible candidate formulations, and we do not know which of them or which combination is correct. A weapon so effective it saved an empire. A formula so secret it died with that empire. And a mystery that has defeated chemists, historians, and military scientists for centuries. The sea off Constantinople still holds its secrets. The Antikythera Mechanism, a computer from the ancient world. In the spring of 1901, Greek sponge divers working off the small island of Antikythera between Crete and the Greek mainland pulled something extraordinary from a shipwreck lying 45 meters below the surface. Among the marble statues, bronze figures, glassware, and coins that had been sitting on the seafloor for roughly 2,000 years, there was a lump of corroded bronze and wood, about the size of a thick hardcover book, that nobody paid much attention to at first. It was clearly a mechanism of some kind. It had gears. But the archaeological world of 1901 had more glamorous things to examine. The lump sat in the National Archaeological Museum in Athens for decades, slowly drying out and fragmenting into 82 separate pieces. Occasional researchers looked at it. Occasional papers were written. Nobody quite knew what to make of it. Then, in 1951, a British science historian named Derek de Solla Price decided to take it seriously. What followed was one of the most remarkable acts of archaeological and scientific detective work in the 20th century. A decades-long investigation that ultimately revealed the Antikythera Mechanism to be something that should not have existed in the ancient world. It was an analog computing device, a mechanical model of the cosmos, a machine capable of predicting solar and lunar eclipses, tracking the positions of the known planets, calculating the dates of the Olympic Games, and modeling the irregular orbit of the Moon, all through an extraordinarily sophisticated system of interlocking bronze gears. And it was built sometime between 150 and 100 BC. Price published his landmark analysis in the journal Scientific American in 1959, and then a more comprehensive study in the Transactions of the American Philosophical Society in 1974. His conclusion, that the mechanism represented a level of mechanical sophistication not seen again in the archaeological record for more than 1,000 years, was initially met with considerable skepticism. It seemed too extraordinary. Gear-based computing machinery in ancient Greece? The technology implied by the Antikythera mechanism did not fit the historical narrative of ancient technological capability. Historians of science had assumed a relatively straight progression from simple ancient tools toward the mechanical sophistication of the Renaissance and Industrial Revolution. The Antikythera mechanism suggested a peak of achievement followed by a catastrophic loss, a technological island surrounded by a sea of less capable tools. The skeptics were silenced, slowly but definitively, by increasingly sophisticated analysis. In 2006, a multinational research collaboration called the Antikythera Mechanism Research Project, involving scientists from Cardiff University, the National Archaeological Museum of Athens, the Aristotle University of Thessaloniki, and several other institutions, applied cutting-edge imaging technology to the fragments. Using three-dimensional X-ray computed tomography and polynomial texture mapping, they were able to read inscriptions hidden inside the corroded fragments and reconstruct the gear system in extraordinary detail. Their findings, published in the journal Nature in November 2006, revealed a mechanism even more sophisticated than Price had described. The back of the device contained two large spiral dials, one tracking a 19-year calendar cycle called the Metonic cycle, one tracking a 223-month eclipse prediction cycle called the Saros cycle. The front displayed the positions of the Sun and Moon against the Greek zodiac calendar, and additional gearing modeled the anomalistic orbit of the Moon, its varying speed as it moves closer to and farther from Earth, using a pin and slot mechanism of remarkable ingenuity. In 2016, University College London researcher Tony Freeth and his team published further analysis, revealing that the front of the device almost certainly also displayed the positions of all 5 planets known to the ancient Greeks: Mercury, Venus, Mars, Jupiter, and Saturn. This required additional gearing of extraordinary complexity, some of which has not survived in the existing fragments. Freeth's team published a complete computational model of the proposed full mechanism in the journal Scientific Reports in March of 2021. Their reconstruction, based on the surviving fragments, the readable inscriptions, and the astronomical knowledge that the mechanism's designers would have needed, proposed a front panel displaying a full orrery of the ancient Greek cosmos, driven by a gear train of breathtaking sophistication. The total gear count in the complete proposed mechanism? Over 30 individual gears, some with teeth so fine that manufacturing them would have required tools and techniques whose existence in the ancient Greek world we have no other direct evidence for. Which brings us to the part of this story that keeps historians of technology genuinely unsettled. We have no other examples. Not one. Ancient Greek and Roman literature contains references to mechanical devices of various kinds. Hero of Alexandria described remarkable automata and pneumatic devices in the 1st century AD, and his writings survive. There are references in ancient texts to similar astronomical computing devices. Cicero, writing in the 1st century BC, described a device made by the Stoic philosopher Posidonius that modeled the movements of the sun, moon, and planets. A device that sounds very much like an orrery. But no physical examples have survived beyond the Antikythera mechanism itself. No comparable gear-based computing device appears in the archaeological record between the Antikythera mechanism and the astronomical clocks of medieval Europe. A gap of more than 1,000 years. This absence is deeply puzzling. If the technological knowledge and craft capability to produce the Antikythera mechanism existed in the ancient Greek world, and it clearly did because the mechanism exists, why do we have no other examples? Why did this technology apparently not propagate, not develop further, not leave a trail of increasingly sophisticated descendants? Several explanations have been proposed. The destruction of the Library of Alexandria, whatever its precise historical nature, likely represented a significant loss of technical knowledge. The political and economic disruptions of the late Roman period broke many chains of craft transmission. The specific social and economic conditions that motivated the production of sophisticated astronomical instruments, wealthy patrons, skilled craftsmen, centers of astronomical learning like Rhodes, where the Antikythera mechanism is believed to have been made, may not have been widely replicated. Alexander Jones, a historian of ancient astronomy at New York University's Institute for the Study of the Ancient World, has argued that the Antikythera mechanism likely represents a tradition of instrument making that was more widespread than the surviving evidence suggests, that we are simply missing the other examples because bronze was a valuable material that was routinely melted down and recycled throughout antiquity. The mechanism survived because it sank with a ship before it could be recycled. This is plausible, but it remains a hypothesis. What is not a hypothesis is the engineering achievement itself. The Antikythera mechanism's pin and slot lunar anomaly mechanism, the component that modeled the Moon's variable orbital speed, is a piece of mechanical ingenuity that modern horologists and mechanical engineers examine with frank admiration. It solves a genuine mathematical problem through a purely mechanical means, using a level of creative engineering thinking that was not supposed to exist in the ancient world. As of early 2026, ongoing analysis of the Antikythera fragments continues. The UCL team has published open-source computational models of the proposed reconstruction. Several institutions have produced physical replicas using modern manufacturing techniques, replicas that work, that display the correct astronomical cycles, that demonstrate the mechanism's functionality. These replicas required the use of CNC milling machines and modern precision manufacturing tools to produce the fine gear teeth to the required tolerances. The ancient craftsmen who made the original had none of that. They had hand tools, files, and extraordinary skill. We can model what the Antikythera mechanism did. We can build replicas with modern machinery. We cannot fully explain how it was built with ancient tools, or why nothing like it appeared again for over a millennium. A computer from 2,000 years ago, sitting in a museum in Athens, still refusing to give up all its secrets. The Great Pyramid, an engineering problem we cannot fully solve. Here is a number that stops engineers cold. 0.05 centimeters. That is the maximum deviation from perfect flatness measured across the base of the Great Pyramid of Giza. a structure covering approximately 5.5 hectares of desert, built from roughly 2.3 million stone blocks, weighing an average of 2.5 tons each, constructed approximately 4,500 years ago. 0.05 centimeters across a base perimeter of almost 1 kilometer. For context, modern construction specifications for high-precision industrial floors, the kind used in semiconductor manufacturing facilities, where even tiny surface variations can ruin delicate equipment, typically allow for deviations of several millimeters across comparable distances. The ancient Egyptians achieved a flatness tolerance that rivals modern precision engineering standards. On desert bedrock, without laser levels, without GPS, without any instrument we have been able to definitively identify in the archaeological record. This is not mythology. These measurements were conducted by professional surveyors using modern equipment. The most comprehensive modern survey of the Great Pyramid's base was carried out by engineer and archaeologist Glenn Dash, working with the Ancient Egypt Research Associates, and published in the Journal of Ancient Egyptian Architecture in 2017. Dash's measurements confirmed and refined earlier surveys, establishing that the base is extraordinarily flat, and that the four sides are oriented to the cardinal directions with an accuracy of approximately 0.05 degrees from true north. 0.05 degrees. Using stars as their only reference points. The engineering puzzles of the Great Pyramid are not one problem. They are a collection of interconnected problems, each individually remarkable, collectively staggering. And modern engineering and archaeology, after 2 centuries of serious scientific investigation, have answered some of them, partially, while others remain genuinely open. Let us be precise about what we know and what we do not. We know who built the pyramids. This is not a mystery. Abundant archaeological evidence, including workers' villages, administrative records, graffiti left by work gangs, and skeletal remains of workers buried near the site, establishes that the pyramids were built by organized teams of Egyptian workers, skilled craftsmen and laborers, not slaves as popular mythology long claimed. Zahi Hawass and his team at the Giza Plateau have excavated the workers' city extensively, and the picture that emerges is of a massive, well-organized state construction project. We know approximately when. The Great Pyramid was built during the reign of Pharaoh Khufu, approximately 2500 BC, give or take a few decades. Radiocarbon dating of organic materials found within the pyramid structures is consistent with this date. We know the basic construction material. The outer casing stones, most of which were removed in medieval times for building material, were Tura limestone, quarried across the Nile. The interior core blocks were local Giza limestone. The granite used in the king's chamber and other interior structures came from Aswan, approximately 800 kilometers to the south. What we do not fully know, what remains genuinely scientifically contested, is the specific methods used to achieve the precision we can measure, and the logistics of moving and placing stones at the required rate. The rate question is particularly challenging. The Great Pyramid contains approximately 2.3 million stone blocks. Khufu's reign is estimated at approximately 23 years, though some estimates range from 20 to 27 years. Simple arithmetic produces a figure of roughly 300 stone blocks placed per day, every day, for the entire duration of the project, to complete the structure within a single reign. 300 blocks per day, each block averaging 2.5 tons. Many of the interior granite blocks weighing between 25 and 80 tons. Moved from quarries across the Nile and from 800 kilometers upstream, raised to heights eventually reaching 146 meters. Experimental archaeology has done valuable work testing specific proposed techniques. In 2014, a team from the University of Amsterdam published research in the journal Physical Review Letters, demonstrating that Egyptians likely used water to reduce friction when dragging heavy stones on wooden sledges across sand, a technique visible in a famous wall painting from the tomb of Jehuti-Hotep, showing workers pouring liquid in front of a sledge. This finding helped explain the logistics of ground transport more convincingly. Research published in 2023 by a team led by Nico de Klerk at Georgia Tech in the journal PLOS ONE proposed that a previously overlooked ancient branch of the Nile, identified through geological survey data, ran significantly closer to the Giza Plateau than the modern river does, potentially providing a waterway for transporting heavy stone blocks much closer to the construction site. This finding, if confirmed by further geological investigation, would help explain one of the most logistically challenging aspects of pyramid construction: the final transport of enormous granite blocks from Aswan. These are genuine advances, real science, moving our understanding forward incrementally. But the precision question remains harder to fully answer. How did Egyptian surveyors establish a base that flat across that area to that tolerance? Several methods have been proposed. Flooding the base area with water to establish a level plane, water finds its own level, and then cutting the bedrock to the waterline, using a grid of channels filled with water as a leveling reference, using A-frame levels and plumb bobs in a systematic survey pattern. All of these methods are plausible with ancient Egyptian technology. All of them have been tested experimentally by various research teams. All of them can produce impressive results in controlled conditions. None of them have been demonstrated to achieve, consistently and reliably, the specific tolerances we measure in the actual pyramid base at the actual scale of the actual pyramid, using only the tools and materials available in 2500 BC. Kate Spence, an Egyptologist at the University of Cambridge, published a significant paper in Nature in 2000 that proposed a specific astronomical method for orienting the pyramid to true north, using the simultaneous transit of two circumpolar stars, Kochab and Mizar, to establish a true north line. This method, Spence argued, could account for the small but consistent offset from true north observed in multiple Old Kingdom pyramids, because the positions of those stars relative to true north shifted gradually over time due to Earth's axial precession. The pyramids' northward orientations, plotted against their construction dates, fit Spence's astronomical model with striking consistency. This was a genuine breakthrough in understanding one aspect of pyramid precision. It also demonstrated that Egyptian surveyors had a sophisticated observational understanding of stellar movement that enabled precision orientation at a level that impresses modern surveyors. But stellar orientation, however sophisticated, does not by itself explain the base flatness, the precision of the interior chambers and corridors, or the engineering of the corbelled granite roof above the king's chamber, a structure that has survived 4,500 years and multiple significant earthquakes without failure. The honest summary of where pyramid science stands in early 2026 is this: we understand more than we did 50 years ago. Experimental archaeology, geological survey, astronomical analysis, and materials science have all contributed genuine advances. The pyramid was built by organized human labor, using empirically refined techniques, not lost technology, not alien intervention, not mysterious forces. But the specific methods that achieved the measured precision, particularly the extraordinary flatness of the base and the accuracy of the cardinal orientation, have not been fully demonstrated experimentally at full scale with period-appropriate tools. The gap between what we can propose theoretically and what we can demonstrate practically remains real. 4,500 years old, still the most precisely constructed large structure on Earth's surface, still not fully. The Baghdad Battery. Did the ancient world discover electricity? In 1936, a German archaeologist named Wilhelm König was sorting through storage rooms at the National Museum of Iraq in Baghdad when he came across a small clay jar that had been excavated near the village of Kujut Rabu, just outside the city. The jar was about 14 centimeters tall. Inside it was a copper cylinder. Inside the copper cylinder was an iron rod, held in place and insulated at the top by an asphalt stopper. The whole assembly dated to somewhere between 200 and 600 AD, the Parthian period of Mesopotamian history. König looked at this object and made a proposal that has generated controversy, scientific testing, and genuine debate ever since. He suggested it was a galvanic cell, a battery. Fill the clay jar with an acidic liquid, grape juice, vinegar, lemon juice, and the copper-iron combination would produce a small but measurable electrical current through exactly the same electrochemical principle that Alessandro Volta used in 1800 when he invented the modern battery. Two dissimilar metals in an electrolyte solution generate a voltage. It is basic electrochemistry. König published his hypothesis in 1938, and the scientific community's response was a mixture of fascination, skepticism, and a question that cuts to the heart of the entire matter. Even if this object could function as a battery, is there any evidence it was actually used as one? That distinction, can versus was, is the most important scientific and historical question surrounding the Baghdad Battery, and it is one that honest discussion of this topic must keep front and center. First, the experimental evidence. The Baghdad Battery hypothesis has been tested multiple times, most famously in a 1978 experiment conducted by German Egyptologist Arne Eggebrecht, who used a replica of the device filled with grape juice and reportedly produced enough current to electroplate a silver statuette with gold. The experiment was filmed and widely publicized. In 2001, the science television program Mythbusters, not a peer-reviewed source, but a reasonably rigorous popular test, constructed replicas of the Baghdad Battery and demonstrated that they could produce voltages of between 0.5 volt and 1 volt when filled with various acidic solutions. This is a small but real electrical current. A series of connected cells could produce higher voltages. The electrochemical functionality of the design is not seriously disputed. If you fill one of these jars with an acidic liquid, it produces electricity. The physics is straightforward. The dispute is entirely historical and archaeological. Paul Craddock, a materials scientist at the British Museum who has studied ancient metallurgy extensively, has argued that there is no archaeological evidence of electroplating in the Parthian world. No objects showing the characteristic thin, even metallic coating that electroplating produces. No residues. No written references to the process. No related equipment. If these jars were being used to electroplate objects, the products of that process should be findable somewhere in the archaeological record. They are not. Craddock and other skeptics have proposed an alternative explanation that is, frankly, more consistent with the known archaeological context. The jars were used for storing sacred scrolls. Clay jars of similar design are documented as scroll storage containers from the same period and region. The copper cylinder and iron rod might have been components of a scroll roller mechanism, or their presence inside the jar might reflect a different use entirely. There is also the question of sample size. Approximately a dozen objects fitting the Baghdad battery description have been identified in museum collections from the Parthian period. This is a very small number on which to build a hypothesis about ancient electrical technology. And none of them were found in an archaeological context that included associated equipment, wiring, electroplating baths, anodes, cathodes, that would be necessary to actually use the electrical current they could theoretically produce. Jason Barlow, an archaeologist specializing in Mesopotamian material culture, who published an analysis of the Baghdad battery evidence in the journal Archaeometry in 2019, concluded that while the electrochemical functionality of the design is demonstrable, the evidence for intentional electrical use remains insufficient to support a strong historical claim. His assessment reflects the mainstream archaeological view. This does not mean Koenig's hypothesis is impossible. It means it is unproven. And here is where the story becomes genuinely interesting from a scientific philosophy perspective. The Baghdad battery sits at the intersection of two different kinds of uncertainty. The first is technical. We know this object can produce electricity. The second is historical and intentional. We do not know if the people who made it knew that or used it for that purpose. These are very different questions, and conflating them is where popular accounts of the Baghdad battery most often go wrong. The enthusiastic version of the story, ancient Mesopotamians had electrical technology, requires not just that the jars could produce current, but that their makers understood what electrical current was, had applications for it, and built a technology around it. None of that has been demonstrated. The skeptical version, these are just storage jars, requires explaining why iron rods and copper cylinders were specifically assembled inside them in a configuration that happens to be electrochemically functional. That explanation exists, but it requires some archaeological assumptions. The honest version sits in the middle. We have objects that are electrochemically functional, found in a historical context where their intended use is unclear, with no direct archaeological evidence of the electrical applications that would make them definitively batteries rather than something else. What does modern science make of all this? The Baghdad battery continues to appear in serious archaeological literature, but always with careful qualification. It is a genuinely interesting archaeological artifact. It raises genuinely interesting questions about the boundary between accidental and intentional technological discovery. And it is a reminder that the absence of evidence for a technology's application is not the same as evidence of its absence. Could a craftsman in Parthian Mesopotamia have noticed that a certain combination of metals in an acidic liquid produced a tingling sensation? Could that observation have led to empirical experimentation with the effect? Could electroplating have been discovered, used in limited contexts, and then lost without leaving a clear archaeological trace? All of this is possible. None of it is demonstrated. The Baghdad battery is real. Its electrochemical functionality is real. Whether it represents ancient electrical technology or a well-preserved storage vessel remains one of archaeology's genuinely open questions. and a reminder that the ancient world was more empirically experimental than we sometimes give it credit for. Small jar, big question. Medieval stained glass, nanotechnology in a cathedral. Stand inside Chartres Cathedral on a clear morning. The light coming through the western rose window does something that no modern glass manufacturer has been able to fully replicate. It is not simply colored light. It has a quality, a depth, a luminosity, a richness that visitors have been describing with inadequate words for 800 years. Painters have tried to capture it. Photographers have tried to photograph it. Glass manufacturers have spent decades trying to reproduce it. And in 1994, a physicist named Giulio Cesare Rigini at the University of Florence decided to stop admiring the effect and start analyzing it. What his team found inside medieval red glass, the deep, blood-red glass found in cathedral windows across Europe, produced between roughly the 10th and 14th centuries, was something that belongs in a nanotechnology laboratory, not a medieval workshop. Gold nanoparticles. Spherical particles of metallic gold, measuring between 5 and 50 nanometers in diameter, millionths of a millimeter, suspended uniformly throughout the glass matrix. Not dissolved, not chemically bonded in the conventional sense, physically suspended as discrete metallic particles, distributed with a consistency and uniformity that modern materials scientists find genuinely impressive. These particles are responsible for the red color. This is a well-understood optical phenomenon called surface plasmon resonance. When light hits gold particles of a specific size, those particles absorb certain wavelengths and scatter others, producing colors that range from deep red through purple, depending on particle size and concentration. The effect was first explained mathematically by German physicist Gustav Mie in 1908, well after the medieval glass was made. The medieval craftsmen had no concept of nanoparticles. They had no atomic theory, no quantum mechanics, no understanding of surface plasmon resonance. What they had was an empirical recipe. Add a small amount of gold chloride to molten glass, control the temperature carefully during cooling, and produce a glass of extraordinary optical quality. Simple in description, extraordinarily difficult in execution. The challenge that modern glass manufacturers face when trying to replicate medieval red glass is not the chemistry in principle. We understand the chemistry perfectly. The challenge is the control. Producing gold nanoparticles of a specific, uniform size, distributed evenly throughout a glass matrix, requires precise management of temperature, cooling rate, gold concentration, and the chemical composition of the glass itself. Small variations in any of these parameters produce particles of different sizes, and different-sized particles produce different colors, or no color at all, or a cloudy, uneven appearance. Research published in the journal Gold Bulletin in 2007 by a team at the University of Aveiro in Portugal analyzing samples of medieval glass from Portuguese churches found that the gold nanoparticles in the best-preserved historical specimens showed a size uniformity that implied extraordinary control of the cooling process. The distribution of particle sizes in the historical glass was tighter, more consistent, than what most modern industrial glass production processes achieve when attempting to replicate the effect. This finding has been confirmed by subsequent studies. A 2013 paper in the Journal of Cultural Heritage, analyzing samples from French cathedral windows, including specimens from Chartres, found similar results. The medieval craftsmen, through centuries of empirical refinement, heating, cooling, observing, adjusting, had arrived at processing parameters that produced nanoparticle distributions of remarkable consistency. Without knowing what a nanoparticle There is an additional layer of complexity that makes medieval glass science even more interesting. The glass itself, the base material, before any metallic additives, was chemically different from modern glass. Medieval glass was made primarily from wood ash and sand, producing what chemists call a potash-lime-silica glass. Modern glass is typically a soda-lime-silica composition. These different base chemistries interact differently with metallic additives, produce different viscosity profiles during cooling, and support nanoparticle formation through subtly different mechanisms. When modern glass manufacturers use modern soda-lime glass as a base and attempt to reproduce medieval red glass techniques, the results are consistently inferior to the historical originals in terms of color depth and optical quality. The base glass chemistry matters enormously, and the specific wood ash compositions used by medieval glassmakers, which varied by region, by season, by the species of wood burned, introduced trace elements that influenced the final optical properties in ways that are still being characterized. Ian Freestone, a materials scientist at University College London, who has spent much of his career analyzing ancient and medieval glass, published a comprehensive review of medieval glass science in the journal Archaeometry in 2015. His conclusion was measured but clear. Medieval European glassmakers achieved levels of optical quality and consistency in colored glass that modern industrial production has not matched. And the specific combination of base glass chemistry, metallic additive concentrations, and thermal processing parameters that produced the finest historical examples has not been fully reproduced. There is a beautiful irony in this story that deserves a moment of. The craftsmen who made Chartres Cathedral's windows were working in a tradition of glassmaking that stretched back through Islamic glassmakers, through Roman craftsmen, through ancient Egyptian and Mesopotamian bead makers, a chain of empirical knowledge accumulated over thousands of years, each generation learning from the last, each generation refining the technique slightly, encoding the refinements not in written formulas, but in the practiced movements of skilled hands and the trained judgments of experienced eyes. When that chain broke, when the Reformation disrupted cathedral building, when wars destroyed workshops, when the specific combination of materials and knowledge that a particular workshop carried was lost, it was lost completely. Not because someone forgot to write it down, but because craft knowledge of this depth and subtlety cannot be fully captured in writing. It lives in the doing. The physicist Giulio Regini, analyzing a fragment of 800-year-old glass with a modern electron microscope, was looking at the preserved record of thousands of hours of empirical experiment, a record written in nanoparticles suspended in silica, by craftsmen who would not have understood a single word of the scientific description of what they had achieved. Beyond the red glass, medieval glassmakers produced other colors through similarly sophisticated empirical chemistry. Cobalt blue, the deep, saturated blue of Chartres' famous Blue Virgin window, was produced using cobalt oxide, with the specific shade determined by the concentration and the base glass chemistry. Green was produced through iron and copper compounds, purple through manganese. Each color represented its own empirically refined recipe, its own specific thermal processing requirements, its own particular interaction between metallic chemistry and glass. Research using modern synchrotron X-ray fluorescence, the same kind of particle accelerator technology used to analyze the Antikythera mechanism, has revealed that the finest medieval colored glasses contain trace element combinations of extraordinary precision. Not just the primary colorant, but secondary elements present in parts per million that subtly modify the color, the clarity, and the optical behavior of the finished glass. Were these trace elements added intentionally? Almost certainly not in any conscious sense. They came from the raw materials, from specific sand sources, specific ash compositions, specific metallic ore deposits. But the craftsman knew which raw materials produced the best results, even if they could not have explained why. They had encoded, through generational empirical learning, a materials science of extraordinary sophistication. A 2022 study from a collaboration between the University of Ghent and the Royal Institute for Cultural Heritage in Brussels, published in Heritage Science, used machine learning analysis of trace element data from over 300 medieval glass samples to identify regional production signatures, essentially fingerprinting medieval glass workshops by their characteristic trace element profiles. The study found that the highest quality surviving specimens clustered around specific workshop traditions, suggesting that particular centers of glass-making excellence had developed particularly refined empirical techniques that produced measurably superior optical results. Those workshop traditions are gone. The specific raw material sources they used have changed or been exhausted. The specific thermal processing knowledge they carried has not survived in recoverable form. And in the nave of Chartres Cathedral, 800 years of light have been passing through glass that contains nanotechnology its makers did not know they were making, producing an optical effect that our best modern science understands completely in theory and cannot fully replicate in practice. That is not magic. That is not mysticism. That is the record of human ingenuity accumulated over generations, encoded in matter, waiting for science to catch up with craft. Conclusion. What 7 mysteries tell us about ourselves. We began this journey with a fragment of Roman glass in a Cambridge laboratory. We end it in a cathedral in France, looking at light passing through 800-year-old windows that contain nanotechnology their makers did not understand. Between those 2 points, we have visited a self-strengthening harbor wall, a medieval sword containing structures from the frontier of modern materials science, a weapon whose formula died with an empire, a computing device that should not have existed for another 1,000 years, a structure of impossible precision built 4,500 years ago, and a clay jar that may or may not be the oldest battery in human history. What do these 7 mysteries have in common? They are all real. Every one of them is supported by published scientific research, by laboratory analysis, by peer-reviewed evidence. None of them requires mystery or mysticism or lost civilizations to be extraordinary. Their extraordinariness is a product of human ingenuity, patient, empirical, generational human ingenuity, accumulated over timescales that dwarf the entire history of modern science. They also share a second common thread, one that is more uncomfortable for our modern technological confidence. We cannot fully replicate any of them. Not because we lack intelligence, not because we lack tools, but because the knowledge that produced them was a different kind of knowledge craft knowledge, embodied knowledge, knowledge that lived in hands and eyes and the subtle judgments of experienced practitioners rather than in written formulas or laboratory notebooks. When the human chain carrying that knowledge broke, the knowledge itself was lost. Not all of it. We can recover pieces, reconstruct mechanisms, understand chemistry. But not all of it. Not yet. There is a lesson here that goes beyond archaeology and materials science. We tend to think of knowledge as something that accumulates steadily, that each generation knows more than the last, that progress is linear, that the tools and techniques of the past are always inferior to those of the present. The 7 technologies we have examined today are a direct challenge to that assumption. Progress is not always linear. Knowledge can be lost. Empirical wisdom accumulated over centuries can be more sophisticated than theoretical understanding developed over decades. And the assumption that older automatically means simpler, that ancient automatically means primitive, is not supported by the evidence. What should we do with this realization? The scientific community is already doing some of the right things. Marie Jackson's team continues their work on Roman concrete. The Antikythera Mechanism research project maintains an open-source model and continues analysis of the fragments. Materials scientists around the world are working on nanotube-reinforced metals, on low-carbon pozzolanic cements, on medieval glass reproduction. The work is slow, methodical, and genuinely exciting. But there is a broader point. Thousands of traditional craft traditions around the world, in ceramics, in textiles, in metallurgy, in construction, in food production, carry empirical knowledge that has never been formally analyzed. Knowledge that encodes, without understanding it, chemistry and physics and material science of real sophistication. That knowledge is disappearing as traditional crafts decline and as the practitioners who carry it age and die without successors. The lesson of Roman concrete and Damascus steel and Chartres cathedral glass is that some of the most valuable scientific information on the planet is not in journals or databases. It is in the hands of people who make things the old way, for reasons they cannot fully articulate, because that is how it was always done. We have electron microscopes and synchrotron X-ray sources and machine learning algorithms. We have every tool that modern science has produced, and we are still learning from people who lived 2,000 years before the scientific method was formalized. That is not humbling. That is extraordinary. The ancient world had something to teach us. It still does. And the classroom, it turns out, has been open all along before the scientific method was formalized. That is not humbling. That is extraordinary. The ancient world had something to teach us. It still does. And the classroom, it turns out, has been open all along.